Today, I want to start from the very beginning of stochastics. Before we talk about variance, correlation, or Brownian motion, we need one basic idea, the idea of a random variable. The name sounds more intimidating than it really is. You already know what a random variable is. You have been using them for years. You just did not call them that. Think about rolling a die. You shake the die, you throw it on the table, and you get a number from 1 to 6. You cannot predict which face will land on top, but still you know the outcome will be one of these 6 numbers. Now think about the return of a stock between today and tomorrow. Right now, you do not know what that return will be. The price might go up, it might go down, or it might stay almost the same. Tomorrow, when the market closes, you will see a concrete number, maybe plus 1.3%, maybe minus 0.8%. These situations have the same structure. Before the experiment, you do not know the outcome. After the experiment, you get a number. That number is what we call a random variable. So here is the key idea in one sentence. A random variable is a rule that assigns a number to each possible outcome of some random experiment. In more intuitive words, take any situation with uncertainty. Tossing a coin, rolling a die, the daily profit or loss of a portfolio, or the number of loans that default in a given year. For each possible way the world can turn out, we attach a number. Heads might become 0, tails might become 1. Each face of the die already is a number. The return of a stock is the relative price change, written as a number. Once we have numbers, we can do math. This is why random variables are so important in finance. Let us look at a few concrete examples. First example, a fair die. The random experiment is clear. You roll the die once. The possible outcomes are the faces from 1 to 6. Our random variable takes the face that shows up and uses that as the value. If you roll a 3, the random variable has the value 3. If you roll a 6, it has the value 6. Simple, but it shows the structure very clearly. Second example, a credit default over 1 year. At the end of the year, either the borrower has paid you back or the borrower has defaulted. There are only 2 outcomes that matter. We describe this with a random variable that takes 2 values. If there is no default, the value is 0. If there is a default, the value is 1. 0 means everything is fine, 1 means default occurred. This tiny 0-1 variable is the basic building block of many credit risk models. When we later talk about the number of defaults in a portfolio, this is what sits underneath. Third example, the daily return of a portfolio. Take the value of a portfolio at the close today and at the close tomorrow. Define the return as the relative change. If the portfolio goes from 100 to 102, the return is plus 2%. If it goes down to 98, the return is minus 2%. Today, you do not know which return will happen. You only know that some values are more likely than others, maybe between minus 3 and plus 3% on a normal day. The rule that takes whatever the market does and turns it into a single number, the percentage return, is again a random variable. So we already have 3 flavors. The die gives us a small set of possible values from 1 to 6. The default indicator has only 2 values, 0 or 1. The daily return has, in principle, infinitely many possible values inside some interval. This leads to a useful distinction. Some random variables take only a finite or countable list of values. We call them discrete. Dice, coin tosses, the number of defaults, or the number of insurance claims all fit into this category. Other random variables can take a whole continuum of values. We call them continuous. Heights of people, exact waiting times, and in many models, the returns or log returns of financial assets are treated as continuous random variables. Visually, you can imagine discrete random variables as separate bars on the screen. Each possible value has its own bar and its own probability. Continuous random variables look more like smooth curves. Instead of bars, you have a density that flows over the real line. The underlying idea is always the same. There is one random experiment and there is one rule that turns each outcome into a number. So why do we care so much about random variables in quantitative finance? Because once uncertainty is written as numbers, the full toolbox of mathematics becomes available. If I represent default as 0 and 1, I can talk about the average default rate in a portfolio, its variance, and its correlation with other risks. On top of that, I represent returns as random variables. I can talk about expected return, measure volatility, and simulate stress scenarios. Without this numerical representation, it would be very hard to build models or to run simulations. With random variables, both become natural. In practice, quant work is full of code that manipulates large collections of random variables. Monte Carlo simulations are many random draws of many random variables, stitched together over time. Risk factors, scenario shocks, simulated losses, all of them are random variables living inside arrays and data frames. So you can think of a random variable as the basic building block of any stochastic model. Everything that comes later in this series builds on it. Expected value tells us where a random variable tends to sit on average. Variance and standard deviation tell us how much it tends to fluctuate. Covariance and correlation tell us how two random variables move together. Random walks and Brownian motion describe how these variables evolve over time. For this first video, it is enough if you remember three things. A random variable is a way to assign a number to each possible outcome of some random situation. Once we have those numbers, we can use math to understand and manage risk. And both simple games like coins and dice and serious financial quantities like defaults and returns fit naturally into this framework. In the next video, we will take the first step beyond the definition and talk about the expected value of a random variable. You can think of it as the average outcome in the long run, or the center of mass of its distribution. We will keep everything visual and connect the formulas back to intuition and to real-world finance.